Hello, everybody. I hope you've had a good week. Let's talk about the spectrophotometry experiment and how to do the lab and how to do the spreadsheet and how to do the graph. So this is an example that I will be using. As always, make sure that you use your own numbers, okay? This is just to show you what to do with those numbers. The numbers that you have should be different, or maybe they're the sum are going to be the same. For example, the stock Fe2 plus concentration that I have here should be the same for all of you. Make sure you check with your classmates. Remember, every time we use something in the lab, you should write down what is on the label. So your stock Fe2 plus concentration should be this, 0.00179. Your maximum absorption wavelength of the complex, that was what we did in the instrument. I don't remember exactly what it was for XX. It was either 512, 522, or 523. So again, make sure that you have that written down. That should be for you. And so then if you see over here, let me see if I can get the pointer. If you see over here, you'll see this is just an M1V1, M2V2 equation. I just already plugged everything in here. So you know what your initial molarity is right here, the 0.0179. This is your M1. Your V1 is this volume right here, converted into liters. Make sure you convert to liters. So there is your V1 or L1. And then this is your volume number 2, 100 mils, because remember we took this Fe2 plus and we diluted it to 100 milliliters in the flasks. And this is going to be your volume 2. So again, M1V1, M2V2. M1V1, M2V2. And if you do that, you should be able to get the number for all of those. You just replace your V1. Everything else should stay pretty much the same. Your absorbance, you should have also recorded those values. That is going to be part of your y-axis when you plot it in Excel. And so it tells you right here, plot the absorbance data on the y-axis, so I just said that, versus the diluted Fe2 plus concentrations on the x-axis. And then from the Beer-Lambert equation and knowing the cell pad length is 1, the slope of this line is the molar absorptivity of the complex. So this is just talking about an equation, which is that the absorbance is equal to the concentration times the path length times the molar absorptivity coefficient. And since we know this is going to be equal to 1, then everything times 1 is itself. This is going to be our x value. This is going to be our slope, m, and this is going to be our y. So once again, we are using the power of linearization and Excel to calculate some measured values. And so your slope is going to be the number you're going to put right here. How do we calculate that? Well, now I'm going to take you to the Excel sheet, and then we are going to see what that's supposed to look like. So here we go. This is the Excel sheet for part A. You see I have different color-coded tables. The green one simply says I have ligand XX. The ligand molarity, once again, I don't really know what that is. You guys should have written that down. So whatever that is, make sure you write it down. I do happen to know the stock concentration of the Fe2 plus. It's 0.00179. And here you see I put a different table for my molar absorptivity. This is the slope. I already have the table down here and the chart. So this number came from the trend line equation that I will show you in a bit. So make sure that you have this somewhere in your spreadsheet to get full credit. You need to report the values that you are deriving. Okay, so this blue table right here, this is just the same table that I showed you guys earlier in the document. You see you have your volume here in milliliters. Yep, your volume of Fe2 plus in milliliters. I converted that to liters because you need to do molarity. Molarity is moles divided by liters. So if you're using milliliters, you have to convert to liters. So then you here in this part, I just said M1V1, M2V2. You see I have my M1 right here, stock Fe2 plus concentration. There's my V1. My V2 is already built in there, 0.1 liters. And when I press enter, all of these values get filled. And of course, here the y-axis is absorbance, starting with 0 all the way to 0.9. And so you go from 1 to 5 milliliters, and then you do your calculations. You get a chart where your absorbance values are on your y-axis. Make sure that this is absorbance. Yes, it is absorption, but it's absorbance. Can't spell. Absorbance. There we go. I think I spelled it right. Concentration is spelled correctly. And so again, your concentration is going to be your x-axis right over here. And then your y-axis is going to be your absorbance, which is going to be this one right here. You're going to insert your graph. You're going to get this chart. You're going to do a trend line. You're going to give me the equation of the trend line. You should get something in the number of the 10 to 15 to 9,000s. You are in the thousands right here. So this right here, example 10,733. This is the number we're looking for. This is the molar absorptivity of whatever the ligand is that we have. And you can see here my R square value. You always want to display your R square value because I want to see how close your data matches to a linear trend. And here we have 0.9998. That's pretty good. So this is what the chart should look like. Make sure you have this. And of course, now that we have that slope value from here, the equation, we can go ahead and put that and report it there. And so then, now that we have this value, if we go back to the procedure or to the worksheet, we can go ahead and actually write down what that is. So again, I said it was 1,733. And so here, it's simply saying, predict what the absorbance would be if you had made 6 mils. So it's the same math that we're doing here. It just goes to 6 mils. So it just becomes 0.006 times the concentration, which was 0.00179. And this is in molar. This is in liters. And again, 0.1 liters. And that is going to give me that answer, whatever that number is, that is going to be my absorbance right here. I don't know what that is. You guys can figure that out. But you see what it is. We're finding out what the equation is, and then we're doing that. So now that we have this, this is going to give me my Fe2 plus concentration, which is just going to be my X value. And so again, now we know from this equation over here, I'm going to use a different color. I'm going to use green. That Y, absorbance, is equal to my concentration, X, which is whatever you got here from this equation. So absorbance is equal to X times the molar coefficient that you just determined times 10733 times the path length, which is 1.00 centimeters. And then that absorbance is going to be the answer that you're going to put in right over there. Okay, so that is how you do part A for this over here. You see here the table for part B shows up. This is different. Make sure that you don't get it confused. The table for part A, if you look over here, the table for part A has concentration versus absorbance. The table for part B has volume versus absorbance. They are not the same thing. They are related, but they are not the same thing. The purpose of part B is we're going to find a maximum absorbance. A lot of you guys, when you were doing this, you said, wait a minute, our absorbance is going up and then suddenly it starts going down again. Yes, that is exactly what's supposed to happen. And so what we're going to do is we're going to plot two lines in one graph. One of those lines is going to be a positive trend line. One of those graphs is going to be a negative trend line. I will show you guys, but make sure you have all of this filled out. This is the table for part B now. And again, make sure you have your new stock concentration of Fe2 plus. Again, I believe this was 0.0015. This you should have calculated from your ligand solution. So stock ligand solution has a molarity, and then you diluted that to 100 based on the direction. So make sure you know your calculated ligand solution. Again, you should know if it's 512 or 523 or 522. One of those two. Talk to your classmates if you don't. And then it says plot the measured absorbance versus the volume of Fe2 plus. And then determine from the intersection the volume of Fe2 plus at which the maximum absorbance will occur. And then it says you have to fit two linear lines and calculate this value. And then you see there's a lot of space over here, and we're going to get to this mathematics over here. So let me switch now to the Excel sheet, and then let's talk about how to do that. So this is for part A. Now I'm going to go over here and switch to the part B table. So again, part B, you see I have a table that shows the green. This is the ligand XX, the molarity. I wish I knew I wish, but one day I will. I know that the stock Fe concentration was a little different too. It was 0.0015 for part B. Make sure you check with your classmates. You should always be writing down exactly what you see. So again, we had a volume of Fe2 plus, we had a volume of diluted ligand, and then from here we have the absorbance values. And so we're going to be plotting that right here, the absorption of your FEXXN ligand versus the volume. And so here, this orange one, this right here shows you as the volume of Fe2 plus is going up from 0 to about 6 milliliters. The absorption is also going up roughly linearly, see? And then it kind of starts tapering off. Here it says it tapers off at 6 mils with a maximum absorbance of 755. And then, as many of you rightfully noted, as the volume of Fe2 plus continues to goes up, the absorbance begins to goes down. So what you're going to do here is when you plot your data, you're going to select two series of data when you're making your chart. You see how here I have two lines of two different colors? These two lines have their own individual trend lines and R values. So this is each a series of data. What I'm going to do is I'm going to look, where is my maximum absorbance? Here, 755 all the way down to 0. So from 6 milliliters down to 0 milliliters, I'm going to use that as my series data 1. And then from 8 milliliters onwards, that is going to be my series data 2. And when I put that in the chart, see if I go to chart design and I go and select data, you're going to see here I have series 2 and series 3. Each one of these data series corresponds to one of these lines. Each one of these lines will give me a trend line. The equation from the trend line both equal to y. You see y equals, let me see over here, we have this trend line right here. Y equals 0.1418x minus this. Over here I have another trend line that also equals to y. Both of these equations are part of the same system, so we can set them equal to each other. And so that's what I did over here. I said the two trend line equations equal to each other. This equation is equals to y, which is equals to this. If I solve for x, once these two equations have been equal to each other, I will get what is called my maximum volume, Vmax. That is equal to my x solution, which in this case will correspond to 5.33 milliliters. That is going to be the volume at which theoretically my absorbance should be the highest. All right. So if I take this x value, this that I just solved for, and I plug it back into either one of these equations, I get a theoretical maximum absorbance of 0.718, which should happen at roughly this volume. However, if you look at the actual data that I measured using an actual instrument, there's a reason we use an instrument. The instrument gives us something real to work with. You see that the highest absorbance in this data set was 0.755. And so just do a percent error calculation. You know, your actual absorbance will be your experimental value, your theoretical value. This is your calculated value. Just do a percent error calculation. This person got 4.9% error, pretty good. And you can see the instructions here that I put down. It says solve for X, calculate minimum percent error using highest measured absorbance, actual versus your calculated absorbance. So actual minus theoretical divided by actual times 100, 4.9%. And so this is what your graph should look like. You have two trend lines, two equations, two R values, both on the same graph. And then you set these two equal to each other and you solve for X. Once you solve for X, you get all of this extra information right there. So once you have all of this information, then you can go back to the worksheet and fill in the rest of the details. So let's go ahead and do that. Let me go back to the worksheet here, new lab manual, and share. Okay. So now that I know where this is, I can calculate the moles of Fe2 plus that I have. So let me grab my actual lab manual here because I already wrote everything out and it'll make things much easier. Okay, so in this case, I said that my maximum volume was going to be 5.33 mils. So 0.00533. Or You notice here the 10 to the 3 is already there. You could just plug it in as you see it. So 5.33, but make sure you do times 10 to the minus 3. Both of these numbers are the same, okay? You're going to multiply that by the concentration of Fe2 plus, which was 0.0015 molar. So that molarity times this max volume, remember, volume times molarity gives you moles. So this is going to give me the moles, which is 7.995 times 10 to the minus 6 moles of Fe2 plus. And this is why I wish I knew what the ligand concentration was, because you're going to do something very similar. So whatever, you find it, whatever that is, that ligand concentration times 20 minus the max volume, and then times 10 to the minus 3. Ooh, I thought I needed to sneeze. Sorry about that. I thought I needed to sneeze. So 20 minus 5.33 times 10 to the minus 3, and that is going to give you your moles of ligand, whatever that number might be. I wish I had that number. I don't have that number. So then you're just going to take your moles of ligand, whatever that number is, divided by your moles of Fe, 7.995 times 10 to the minus 6 moles of Fe. And this number is expected to be in the vicinity of 3. So it should be 3, 3.10, 3.20, 2.8, somewhere hovering around 3. Hopefully that makes some sense. And this is how you get these numbers from that. So then moving on to the question, now that we've calculated what this n number right here is, we can go ahead and actually answer the question right here. So this question is going to get a little bit complex, so just bear with me. Make sure you pause and you go back in the video as necessary, okay? So here we go. So first, we're going to start with the n value that we just calculated. Again, for example purposes, I'm going to just go ahead and say that this is 3, okay? So let's say that this n is equal to 3. Use whatever number you actually end up calculating, okay? So that means I have 3 moles of ligand for every mole of Fe2 plus. It's just a molar ratio, really. It's as if we were doing an equation. We just haven't used the formula. So it says, predict the absorbance of a solution made using, look, here's a volume, here's a molarity of Fe, and look, here's a volume, and here's a molarity of ligand, diluting to 100, here's a V2, pretty similar to the calculations that we just did. And then they even give you a hint. It says, it is important to take into account the n value, well, I already did right over here, determined above, as well as the molar absorptivity constant, which we determined earlier. So 10,733 per molar centimeter. There we go. All right. So first, we got to figure out which is our limiting reagent. Is it our Fe2 plus or is it our ligand? Well, let's see. It's ligand, moles of ligand over moles of Fe, and it's supposed to equal roughly somewhere close to 3. So let's start with the ligand. It says we have 8 milliliters of ligand, so 0.008 liters times 0.456 times 10 to the negative 3 molar. That is going to equal to, let me do my calculation, 3.648 times 10 to the minus 6. 648 times 10 to the minus 6. And this is going to be moles. Okay, so this is how many moles of ligand I actually have. Moles of ligand I actually have. Okay, this came from the equation up here. And so I'm also going to do the same thing for moles of Fe. So for moles of Fe, let me use another color. Fe is orange, so I'm going to use orange. So 0.012 times 0.345 times 10 to the negative 3 molar. And again, volume times molarity gives me moles. What is that number? I think it was 4.14 times 10 to the minus 6. And this is moles of Fe2 plus that I actually have. Okay, sounds good. So this is how much I actually have. Now I have to figure out which of the two is the limiting reagent. Well, let's go ahead and start with the ligand. So this number right here, let me go back to red. So 3.648 times 10 to the minus 6 divided by x, which is going to be our moles of Fe hypothetical, is equal to roughly 3. Well, if we solve for that, my x is going to be 1.216 times 10 to the minus 6. 1.216 times 10 to the minus 6 moles of Fe2 plus needed. So this is how many moles would be needed to react with the moles of ligand above. And I'm going to do the same thing with the moles of Fe down here below. So I'm going to go ahead and let's see. X would go on top this time because the Fe is at the bottom. Let me go ahead and close this menu. So then we would have X at the top, and then we have 0.012 times 0. Oh yeah, I already calculated that number. Sorry about that. Let's just go ahead and say X 4.14 times 10 to the minus 6. And that number came from here. Remember, we solved for it before we did this right over here. And that is going to be equal to roughly 3. So if I do that, my X value should equal to 1.242 times 10 to the minus 5. 1.242 times 10 to the minus 5 moles of ligand. Okay? So this is the moles of ligand that would be required to react with the moles of Fe. And up here, this is the moles of Fe that would be required to react with the ligand. Which one is the limiting reagent? Well, let's see. The ligand needs times 10 to the minus 6 moles of Fe2 plus, and we do have times 10 to the minus 6. We have roughly 4 times as much. 4.14, 1.26. So we do have enough Fe to react with this theoretical mole of ligand. Do we have enough ligand to react with this theoretical mole of Fe? Let's see. This moles of Fe would require times 10 to the negative 5 moles of ligand. But we only actually have times 10 to the negative 6. In other words, it is going to be the ligand up here that is your limiting reagent. Okay? So only this many moles are going to actually create the ligand complex. Please talk your way through this. Talk your way through this. This is just another way of doing a limiting reagent problem. This is the amount of Fe that is going to actually react with the ligand to form something that will absorb, and that is what is going to absorb and measure it. So now we have the moles of Fe2 plus, and then we also have our V2. So we have 1.24. Oops, not that number. There's the other number. Sorry about that again. I need to switch the pen back to red. Here we go. 1.216 times 10 to the minus 6 moles of Fe2 plus divided by the new volume, 0.1 liters. That is going to give me 1.216 times 10 to the minus 5. And that is going to be in molar. And you are going to multiply that number by your molar absorptivity constant. And that is going to be times 10,733. And that is molar to the negative 1. That cancels out your molars, and you get 0.130. And that is your absorbance. That is the answer, 0.130 right there. So just talk your way through the math. It's actually not as difficult as this makes it out to be. It's just that you're used to seeing limiting reagent problems with a chemical reaction equation. And there is one. If you scroll up to the sheet, let me see if I can scroll a little bit faster. You'll actually see it right here. See? You're just doing this equation. You're figuring out what that n number is right there. So it's just another way to do so. So just don't get discouraged. Come to office hours, ask questions. But there you go. So once you have that, I'm going to share the Excel sheet one last time. Make sure you have your equations, your R-squared value. Make sure you have everything labeled properly. Make sure you have your graphs scaled properly. I don't want to see extra space that doesn't have any data in it. It just makes your graph look smaller and tackier. Okay, make sure you have all of the stuff you're required to do, all the information that you need. Make sure you have good organization. Other than that, unless I am missing anything else, I don't believe that there's anything else that you have to write or report about. I think once again that the instructions from the lab manual are pretty straightforward. So follow that or ask me if you have any additional questions. I hope that this was useful and helpful. I will see you guys this coming week, and I hope you guys have a good night. So thank you for your attention, and we'll see you later.